How do we calculate the steps in recurrences, and how do we get the bound? Let's first define a recurrence or recurrence relation. A recurrence relation is an equation or an inequality that describes a function in terms of its value on smaller inputs. An example is the following. T of n is equal to a times t of n over b plus f of n. As you can see, t of n is described by a function with smaller input, as you can see here. So its definition calls to itself. We'll primarily study recurrences of this form. Our first way to simplify recurrence relations is by using the iteration method, also known as the unrolling method. This is done by expanding the recurrence and expressing it as a summation of terms. Let's have a sample recurrence relation. T of n is equal to n plus 2t of n over 2. This is actually the recurrence relation for merge sort. As you can see, we have two recursive calls right here, 2 times t of n over 2, which are the two merge sort calls, and n is the cost of merging. Using the iteration method, we have to keep expanding the recurrence until we can no longer expand further. So let's first expand t of n over 2. So what is t of n over 2 equal to? Remember that this is a recurrence and we already defined what t of n already does. So it's only a matter of substituting n over 2 to n. Let's illustrate. So let's switch here. As you can see here, is the same definition. T of n is equal to n plus t of n over 2. So it's only a matter of what is t of n over 2 equal to. So t of n over 2, basically in that case, you have to substitute n over 2 to n in our definition. So you could think of it as something like this. T of blank is equal to blank plus t of blank over 2. For all instances of n, as you can see here, you replace it with whatever you put here. Okay, so if you put something here, let's say x, you put here x, and you also put here x. You'll replace all instances of n. In our case, we'll put here n over 2. So we'll put here n over 2, and then n over 2 here, and also n over 2 here. Like so. Again, whatever you put here, you also put here and here. Okay? So t of n over 2 is equal to n over 2 plus t of n over 2 over 2, which is thus equal to n over 4. Okay? Now that we know what t of n over 2 is equal to, we could just simply expand that to something like this. So t of n over 2 is equal to n over 2 plus 2t of n over 4, and you have two instances of that. Let's simplify a bit, but let's not fully simplify. So we'll get something like this. So n plus 2 times n over 2. That's when we distribute 2 to this one, to this term here. And let's distribute 2 to this term here. So that's 4t of n over 4. And now, to continue, we simply have to find out what is t of n over 4 equal to. And as you can see here, we now have 4 recursive calls, with each passing a size of n over 4. So what is t of n over 4 equal to? Okay, let's go back here. So we already know what t of n over 2 is equal to. Now, what we want to know is what is t of n over 4 equal to. So again, we just have to put here n over 4, and whatever we put here, we also put here and here. We simply replace all instances of n with n over 4. So n over 4 here, n over 4 here, and also n over 4 here. So something like this. T of n over 4 is equal to n over 4 plus t of n over 4 over 2, or simply n over 8. Now that we know what t of n over 4 is equal to, let's substitute that here. So we'll get this whole expression. So 4 times n over 4 plus 2t of n over 8. And again, let's simplify a bit, but not fully simplify. So distribute 4, and we'll get this 4 times n over 4 plus 8 times t of n over 8. So we just have to continue expanding or iterating until we can no longer iterate or expand. But the question is, how far must we iterate? Remember that this is the recurrence relation for merge sort. So initially, we have two recursive calls with half and half of the array as input. So you can see here, we have an array containing some numbers. In order for us to sort this, we have to pass it through two merge sort function calls, recursive calls. So something like this. So merge sort will cut this in half, one half here, one half here, and the recursive call goes on again. So we'll continue calling merge sort, but this time for half of this and also half of this. So technically speaking, we have now 4 recursive calls, like what happened earlier. And this will continue until we get to this. And this are our last recursive calls. So why did merge sort stop recursing here? What's the reason? Why did we stop here? What do you think? The reason is, it's because we reached the point where we can no longer divide the array. As you can see here, we reached the individual elements. At this point, we have reached the base case, and we will now start merging back in order for us to sort the array. So going back here, what is the answer to this question? It's the same answer actually. So the ith term is 2 raised to I times n over 2 raised to I. Now, where did we get this? Let's go back a bit. As you can see here, we have a pattern. So you could actually imagine this n as 2 raised to 0 over 2 raised to 0 times n. This is 2 raised to 1 over 2 raised to 1 times n. This is 2 squared over 2 squared times n, and so on and so forth. So that's how we got this term. And the ith term is the last term. And therefore, the iteration stops when n over 2 raised to I, this term here, is equal to 1. Again, this first term is the number of recursive calls. As you can see here, we have 2 recursive calls, 4 recursive calls, and so on. And this is how we divide the array. For example, n over 2, that's the first halves, and this is the when we divided it by 2 again, so we have 4, and then so on and so forth. So this is how we divide the array. So the iteration stops when n over 2 raised to I is down to the individual elements. N over 2 raised to I is equal to 1. So we simply have to find out what is I equal to. So let's solve for that. N over 2 raised to I is equal to 1. 2 raised to I is equal to n. We just switched it. And I is equal to log of n base 2 when we log both sides here. So that means that the final step is the log of n base 2 step. So if we expand our recurrence fully, it'll look like this. So n plus 2 times n over 2 plus 4 times n over 4 plus 8 times n over 8 plus dot 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 plus 2 raised to log of n times n over 2 raised to log of n. We could actually simplify this directly. We know that these terms here will cancel out, so we'll be left with n, but let's express it first as a summation. So it's the summation of 2 raised to I times n all over 2 raised to I, where I goes from 0 to log of n. Take note we start at 0 because, as you can see here, this is equivalent to 2 raised to 0 over 2 raised to 0. 2 raised to 1 over 2 raised to 1, 2 squared over 2 squared, and that's why we started with 0, and so on, and we'll end at log of n. So let's simplify. So this will just cancel out. This is just equal to 1, like so. we can factor out n here, like so. And now we have here log of n plus 1, because 0 to log of n, number of ones. Or we could just simplify that to n log n. And that's O of n log n. So technically that's n times log of n plus 1, because that's 0 to log of n, not 1 to log of n. But this makes it simpler. And we're using asymptotic analysis anyway. So this recurrence relation, let's go back here. Oops, here. Is just equal to n log n, or O of n log n.